Our last three targets of this unit are all going to be about what's called linear programming. So we're just going to do targets 12 and 13 today. Target 14 will be next class. So linear programming, what we're going to be doing is using a system of inequalities, which you guys have graphed. And we're going to figure out in that system of linear equalities, where can we find like a maximum or a minimum amount? So first of all, linear programming allows us to represent a situation using multiple linear inequalities, so a system of them. And in the real world, there's lots of constraints on situations. So when you think about an inequality, a lot of times we're talking about like situations that can't involve negative values. So if we put meanings behind our linear inequalities, then we could say things like if you're solving for the amount of nickels and dimes, you can't have a negative amount of nickels or a negative amount of dimes. That doesn't make sense. Also, there's just restrictions. Like if you're trying to build a company, there's cost restrictions to that. There's money restrictions, space restrictions. So in our reality, there's lots of restrictions on things that we want to do. And so inequalities can help us represent all of that. And so when we put those linear inequalities together, we have linear programming. So it allows us to take these restraints into consideration while still maintaining that we will want to maximize or minimize the outcome of a situation depending on the context. For example, we want to minimize cost, but we want to maximize profit. That would just be a really basic example of that. So whatever our context is or whatever our goal is going to be determined by what's called the objective function. Our goal is to test some different points to determine if a maximum or a minimum occurs. If it does, it will happen at the vertex of the feasible region. So this is a lot of new information here, and we're going to walk you through it as we go through each of these problems. So what's given on this first target? So for target 12, we've given you the feasible region. So basically when you're looking at A and you see that shaded region on the graph, that's the solution to the system of inequalities. So instead of just graphing two inequalities and looking for the double shaded region, there are actually 4 linear inequalities graphed here, and this is the quadruple shaded region that we're looking at. So that's what we call the feasible region. That's the shaded region. The objective function is up here. So the objective function is a linear function, and we don't have any context to that right now, so we don't know what it means. Is it talking about the cost of something or the space of something? But whatever it is symbolizing whatever we want to maximize or minimize. So the way we're going to go about this is if there's a maximum or a minimum value, it's going to occur at one of the vertices. And so we're going to go around, and the vertices are the corners, and we're going to take each of these vertices and we're going to list it here. So that point was -1, 0. And then what we're going to do is plug it into the objective function. So we have an x value and a y value from the vertex. And I'm just going to plug that into the objective function. So that would be c equals 3 times -1 for x plus 4 times 0 for y. And I'm going to simplify that. So -3 plus 0 is -3. And I'm going to do that for all the 4 vertices here. So I'm going to pick, it doesn't matter the order you go. So now I'm going to pick 1, 3, plugging 1 in for x and 3 in for y. So the output there would be 3 plus 12, which is 15. Continuing around, I have 3 and 2. So c equals 3 times 3 plus 4 times 2. So that would be 9 plus 8, which is 17. And then our last vertex is 4, 0. So I'm going to plug that in. So that would be 12 plus 0, which is 12. So then we're going to go up and we're going to answer the question about the minimum and the maximum value. So the smallest output was right here. So the minimum value is -3, and that occurred at the vertex -1, 0. The maximum value, the maximum output, is 17, and that occurred at the vertex 3, 2. And so that's all we're doing here on target 12. And so the kind of confusing thing is eventually we're going to put some meaning to x and y like we did earlier in the unit when we wrote our systems of equations given a word problem. And so it'll make a little bit more sense, like the minimum value, like are we talking about cost? Are we talking about profit? And like what does X represent? What does Y represent? So we'll get to all of that, but for right now we're just getting used to taking a look at a feasible region, that shaded region, picking out the vertices and testing them in the objective function. All right, so this is the same idea, it's just a different equation, different feasible region. So remember the objective function is that c equals x plus 2y, so that's what I'm going to keep going back to. So pick one of your vertices. It doesn't matter the order you do this. So I'm going to start with 0, 5, and I'm going to plug that into the new objective function. So c equals x, which is 0, plus 2 times y. So this would be 0 plus 10, which is 10. Notice the scale on this graph is by 2's. So that point is 3, 3. So c equals x plus 2y. So that would be 3 plus 6, which is 9. Then I'm going to pick the point 5, -1. So c equals 5 plus 2 times -1. So that would be 5 plus -2, which is 3. And then the last vertex is 0, 2. So 0, -2. So c equals 0 plus 2 times -2, which is -4. Okay, so looking at our questions, the minimum value is -4, and that occurred at the point 0, -2. And then the maximum value is 10, and that occurred at the vertex of 0, 5. So again, just kind of prefacing what's to come. So this feasible region will actually represent a situation or a series of restrictions on a situation. And so if there is a maximum or a minimum, so if there is the best way to maximize profit or the best way to minimize profit, it's going to occur at one of these corners. So that's why I'm picking these points specifically, and I'm not picking a point like right there that isn't on a vertex. I'm only interested in those vertex points. So we're going to amp it up a little bit once we get to target 13. And so on target 13, what's going to happen is we're actually going to graph the constraints, and we're going to find the feasible region. It's no longer given to us. So you can see that we're given an objective function just like we were on the last problem, and we're given some constraints instead of the actual graph. So we'll create this graph. So the first constraint says x is greater than or equal to 0. So on our graph, x equals 0 is this vertical line on the y-axis. And it says x is greater than 0, so we're going to shade to the right. So it's everything bigger than 0. And then it says y is greater than or equal to 0. So the line y equals 0 is on the x-axis. It's a horizontal line. And it says y is greater than or equal to 0. So we're going to shade above. So really, these two constraints, these first two constraints, are just saying you're talking about all positive numbers. So if our graph, if the given graph was like all 4 quadrants, we would have only shaded quadrant 1. But because this graph is drawn the way it is, it does look like we're shading the whole graph. Now for this last constraint, it's not in slope-intercept form, so I'm going to subtract the x. So it's y is less than or equal to negative x plus 4. So when I go to graph this, it's a y-intercept of 4, 1, 2, 3, 4, and a slope of negative 1. And then it says y is less than, so we're going to shade below. And so our feasible region is going to be the region where all three of these inequalities were shaded, which is this triangle right here. And then when it comes to the vertices, we can actually figure out what those are. So this vertex, this corner, is at 4, 0. This vertex is at 0, 0. And this vertex is at 0, 4. Those are the only 3 points we're interested in because those are the corners of that triple shaded region. So when we go to test our vertices, so now basically now we're picking up where we did on target 12. So pick one of your vertices, it doesn't matter which one. So I pick 0, 4 first, and then test it in that objective function. So c equals 2 times 0 plus 4, that's 0 plus 4, which is 4. Pick another one of your vertices, plug it into the objective function. That simplifies to 0. And then our last one is 4, 0. So plugging that in, that would be 2 times 4 plus 0, which is 8. So the minimum value is an output of 0, and that occurred at the point 0, 0. And our maximum was 8, and it occurred at the point 4, 0. So we're going to do another one just like that. Notice the numbers do change a little bit here, but other than that, this is just the same. So we have a new objective function, and then we're going to have to graph these constraints here. So this first constraint looks kind of strange. So 2 is less than or equal to x is less than or equal to 4. So because it's x, that means these are vertical lines. So we have a vertical line at 2, and we have a vertical line at 4. And because the x is in between, that means that we shade in between these two lines. So we're looking at that region right in there. Then for our second constraint, it says y is greater than or equal to 1. So I'm going to make a horizontal line at 1. And it says greater than, so I'm going to shade above. So I'm keeping in mind where right now the double shaded region is. It's anything where there's red and blue. And then we have this last equation, or inequality, and I've got to put it in slope-intercept form. So y is less than or equal to negative x plus 5. So I'm going to go up to 5, 1, 2, 3, 4, 5, and a slope of negative 1. Okay. And it says y is less than, so I'm going to shade below. Okay, so this feasible region is really small. If you look wherever there is just red, green, and blue, it's this triangle right here. So I'm going to actually go ahead and come on over here and write what the vertices are instead of trying to make that graph messier than it is. So we have a vertex at, it looks like it's 2, 1. And remember, the vertex is just the corner of the graph, or corner of the shaded region. Then it looks like there's one at 4, 1. So I've got 2, 1 right there, 4, 1 right there, and then this point is going to be 2, 4. So that's the last vertex, the last corner. And now I'm going to go ahead and test all of these in my new constraint function. So C equals negative 3 times 2 plus 5 times 1. So that would be negative 6 plus 5, which is negative 1. Then for the vertex of 4, 1, C equals negative 3 times 4 plus 5 times 1. So that's negative 12 plus 5, which is negative 7. And C equals negative 3 times 2 plus 5 times 4. So that would be negative 6 plus 20, which would be 14. So the minimum value, the smallest value, is negative 7, and that occurred at the point 4, 1. And the maximum value was 14, and that occurred at the coordinate of 2, 4. And that's your notes over targets 12 and 13. We'll pick up with this in target 14 and put a little bit more meaning to these problems.